Okay, hello everyone. As promised, here's the 15.3 video. So 15.3 is the next natural step in our integral for multivariable functions. So really, we're still concerned with domains in R2. So in 15.1, we started out with just integrating on simple rectangles, right? And then 15.2, we started considering regions that were kind of bounded by these like functions, like maybe, the y bound is this line, y equals negative x plus 5. And so we had kind of a little bit strange bounds like that. And that takes us to a certain point. And then this using polar coordinates to integrate is kind of another useful tool that we're going to develop. And you might think at first that it's really just kind of difficult and unnecessary, but it's an extremely useful tool. And I'll kind of explain the context when appropriate. Okay. So that's just what I've said now. The reason that these polar coordinates, well, let's first talk about the limitations of Cartesian coordinates. Cartesian, meaning our xy coordinates, they're all well and good, but there's some cases where they don't work as well, right? And we saw this in Calc 2 when we started talking about polar coordinates for the first or second time. Remember in Calc 2, we had these shapes like the clover, the kind of four-leaf clover thing, this would be really hard to describe in Cartesian coordinates, right? It's not a function of x, it's not a function of y, but we could write this as a polar equation. And I honestly don't even remember what let's see, what is the polar equation? It's something like sine of 4 theta or something like that, or cosine 2 theta. Yeah, so this one would be, this is a function, it's in polar coordinates, it's cosine of 2 theta. Okay, so we have this, and this is a relatively simple function, right? R equals cosine of 2 theta. It's not some crazy thing involving all kinds of ugly terms. It's really simple, and it gives us this seemingly very complicated shape. So these polar coordinates are a powerful tool, and they're especially powerful when our functions are kind of oriented around the origin. Okay, and what I mean by that is, like, all our function, like in this function, for example, okay, what is this function saying? It's saying r, which we can think of as our distance from the origin, is a function cosine 2 theta, where theta is our angle measured from this horizontal axis. So these polar coordinates are naturally kind of oriented around the origin, and that makes them a really powerful tool for considering functions with, kind of a circular symmetry, or a symmetry around the origin. So, functions like, or curves like circles, this is a very simple function. Like if this has radius, 4, it's just r equals 4. Okay, that's and this is a function, whereas this would not be a function of x or y, right? So these polar coordinates deal really well with things with kind of some symmetry around the origin, and Cartesian coordinates kind of have trouble with that, right? Now you might be wondering, okay, well, why do we care? Well, stuff with this type of symmetry pops up a lot in the physical sciences, engineering, physics, things like that. You might have heard of partial differential equations, PDEs. there's a couple famous types of PDEs. Like PDEs are divided into these kind of general classes. We have like the wave equation and the heat equation that just get used all the time. And you modify them a little bit as necessary for your particular situation. But these things have this this symmetry. For example, if you're considering, let's say you have a source of heat. We're talking about, we said the heat equation. Okay, let's say you have a source of heat. Okay, the heat, and then you're kind of measuring the temperature in a region around that source. Well, let's say this is 100 degrees. Okay, your region, the temperature of the surrounding region is really symmetric around that source. Like, it doesn't really matter. The x and y coordinates aren't too important. What's more important is just the distance from your source of heat, right? So naturally, it becomes often very convenient to use polar coordinates. Okay. So as I was saying, Cartesian coordinates, they're nice. The x and y coordinates are nice because they're very familiar, but they can be a little limiting. So, for example, consider integrating this function. Okay. Let's say our region is the circle centered at the origin with all the points less than or equal to 1 unit away from the origin. Okay, so this is just our region, right? Our domain, our region R. Okay, so we're integrating this function on that region, and maybe in this case we could write the region fairly easily in terms of x and y, right? Using your techniques from 15.2, maybe we would write this region, make the x bounds our actual numbers, and then the y bounds would be our functions, right? So what would our y bounds be? Well, try and solve it yourself, but it would probably look something like this, right? Because what is this curve here? This curve is the circle x squared plus y squared equals 1. So really what you would have to do is kind of split this one circle into two different functions. Okay, you would split it into like this top function, the circle, the equation for the circle is not a function, but if you consider these individual pieces here, those two curves are circles. Okay, so that top curve we could write as y equals positive square root of 1 minus x squared, and then the bottom curve we could write as negative square root of 1 minus x squared. Okay, and so we could write our bounds for our integral fairly easily, but then integrating this function would be really hard. Okay, so in this case, maybe the problem is not the bounds, but how do we even go about trying to integrate that function? Okay, and this is a function that should be fairly easy to integrate using polar coordinates. It should only be, it should almost be an immediate integral. It should be very easy. Okay, so we can maybe see maybe you don't see, I haven't taught you how to integrate this in terms of polar coordinates yet, but maybe you can see the difficulty. Okay, this will be a very hard integral in Cartesian coordinates. So it's kind of a motivating example, right? We want to develop a new tool. Okay, and as I said, the problem is that these Cartesian coordinates don't really deal well with functions that are kind of oriented around the origin and this kind of, circular orientation. That's my term. You're probably never going to see it again, but it's, kind of got some symmetry around the origin. And as we already said, that we learned in Calc 2, these polar coordinates, these polar functions are a good way to kind of overcome these difficulties. Okay, so we're gonna develop a theory of integration, and we're not developing a new theory. We're just gonna kind of extend our existing theory to modify it a little bit to include functions of polar coordinates. Okay, so if you need a little review of polar coordinates, my YouTube channel has my Calc 2 lectures from last semester, which includes polar coordinates. We don't need to be able to work with polar functions, I wouldn't say, to the extent we did in Calc 2. Like, I'm not going to ask you to really differentiate polar functions and graph these weird four-leaf clovers and limicons and things like that. We have to work with them a little bit, so you don't need. If you remember it all, great, but just take a little while and just get the basics down if you need to do that for the rest of this material. Okay, so we're going to start by, well, before I kind of introduce this material, let's kind of talk about what the goal is. Okay, in this section, we want to essentially, really the big tool we're going to develop is we're going to start with a function of xy that is hard to integrate. And then we're going to convert function and region into polar coordinates. And then integrate in terms of polar coordinates. Okay, so maybe these two steps we could do already. What we need is, how do we integrate in terms of polar coordinates? Okay, so let's talk about integrating in terms of polar coordinates. And we're going to talk about this before we talk about converting from Cartesian to polar. So we're just thinking about polar functions right now. Okay. All right. So remember in like 15.1, 15.2, well, especially 15.1, we were concerned about integrating on a rectangle, right? So where we had like a region that was kind of described like this, where x is greater than or equal to a and less than or equal to b, and y is less than or equal to c, and greater than or equal to c and less than or equal to d. And this is how we describe our rectangle. And what does that look like? It's a rectangle. So let's say we have our xy plane. I got a to b and c to d. Okay, and then we have a rectangle here, right? That's our rectangle. Okay, and rectangles are really how we developed our multivariable integral, right? If we have a region, even if it's kind of a complex region, something like this, we essentially break it up into rectangles, and we consider the boxes in each rectangle that approximate our volume, and then we take the limit as our area of the rectangles gets really small, and that gives us our integral. Okay. Now forget about the picture for a second and just think about these bounds, right? X is greater than or equal to a and less than or equal to b. Y is greater than or equal to c, less than or equal to d. What if we did the same thing for polar coordinates? So let's say, remember, we have, for polar coordinates, we have our r and theta, okay, where this is our radius, and theta is our angle from the horizontal axis. Okay, what would these bounds give us. Okay, so let's say r is greater than or equal to alpha and less than or equal to beta, and theta is greater than or equal to gamma and less than or equal to delta. Okay, what would those kind of bounds give us? Well, we're going to call it a polar rectangle. It's not really going to be rectangular looking, but just because we call this thing a rectangle in Cartesian coordinates, we're going to call something like a region like this, we're going to call it a polar rectangle. Now, what would it actually look like? It's actually going to be kind of a chunk of a circle. Okay, so maybe I didn't, maybe my drawing doesn't convey that, but essentially think about kind of two concentric circles, and I'm just going to draw a quarter of them. So think about two circles, okay? And then let's say let's say they go all the way around, right? Okay, what would theta between gamma and delta mean? Meaning like my angle, I'm considering angles, let's do this in blue. I'm considering angles between okay, so this angle would be like our what, gamma, and then this angle would be like our delta. Okay, so those are my my region is somewhere between those two angles. And then what I'm saying for r is that my r is between alpha and beta. So my r is between, r is my distance from the origin. So r is between alpha and beta. And then I combine those conditions, and what do I end up with? I end up with this region, which we call our polar rectangle. Okay, so that's what my polar rectangle looks like. Now, remember how we developed the theory of our multivariable integral? We started with rectangles, right? Okay, even if let's say I want to consider let's say I have some function fxy, and I want to consider, whatever the volume beneath the curve on this region, on this rectangular region. So we start out about considering this rectangular region, right? Okay. So, and let's say my function looks something like, whatever. Okay. It's not really to scale, but let's assume that this region is directly above my rectangle. Okay. Okay, so let's say our region looks like this. Okay, remember how we consider the volume beneath that surface for our rectangle. Basically, what I do is I divide that my domain, my rectangular region. I divide it up into well, smaller rectangles. And then I consider, you know, the boxes. I approximate my volume with a bunch of boxes, essentially, right? Okay. And I add up the volumes of those boxes, and then I take the limit as those boxes get really small, and that gives me my exact volume. Okay, so the first step, and then we're doing the same thing for polar coordinates, but as you can see, the first step for this Cartesian stuff was figuring out just the volume of a box, right? And for our Cartesian stuff, the volume of the box, well, it's just the area of the base times the height, which is like the function value. All right. So we're going to develop a similar theory or similar technique for polar coordinates. Okay. So that was the this is the volume of our box in Cartesian coordinates. And how did we write it? We wrote it like fx star fxi star yj star. What is that? That's the height of my box. And what I do is I just pick a point in my box and then plug it into my function, and I call that the that gives me a height, and I call that the height of my box, right? And then what is this delta A term? Well, that's the area of my base, okay? And that area, we could, you know, consider that as delta X times delta Y, the length of the box times the width of the box. Okay. And then remember where we went from there. You know, if I have some complicated region, I just break it, you know, if this is our domain, we break it down into smaller rectangles, and we consider the volume of each box where the base is one of these rectangles, and we add them all up and we get our volume, and then we take the limit as our area of our base gets really small. And as we take the limit, the double sum becomes a double integral. This these functional values become fxy, and then this term, this delta A, well, that's going to become our dA, which is really, you know, dx dy, right? Okay. So we're going to progress along the same path. So first step is figuring out how to calculate the area of just one of these boxes, right? Okay, but we're going to do that for polar rectangles. Okay, so we're considering a polar rectangle now. Okay, so let's say I have a region like this. I'm going to essentially break it up into a bunch of polar rectangles. Okay, so I have a bunch of, you know, radiuses and a bunch of angles, and this gives me a bunch of polar rectangles, and I'm going to find the volume on each of these polar rectangles, and then I'm going to add them all together. But my first step, as I said, is just finding the volume on one of these polar rectangles. Okay. So what is the volume of that polar rectangle going to look like? Well, my function of my polar coordinates is still going to give me, okay, let's say this point in polar coordinates is in my polar rectangle. Then my function at those at this point is still going to give me the height of my object. And then essentially what I'm doing is I'm going to multiply by the area of the base, okay, which we would call delta Aij, okay, the area of my base, and that's going to give me the volume of my, you know, box, or, you know, kind of generalized cylinder, if you want to call it that. So the function, you know, finding the area or finding the height is not a problem, right? We just plug some point in our polar rectangle into our function, and that gives us our height. The problem is really, what is the area of each of those polar rectangles? What's the area of something like this? Okay. Now, how do we think, we can think about this polar rectangle. Really, we can think about it in terms of like sectors of a circle, right? And it's really going to be the difference of two sectors of a circle. Okay, so let's say we want to find the volume of this thing. Okay, well, that polar rectangle, okay, how could I think about that? Think about this blue slice of our circle, of a circle. Okay, right, I have this blue slice, and that has, that volume is, or excuse me, that area is easy to find, this blue volume here. I use the formula for the sector of a circle, okay, which is going to be this. Let's call it depends on the radius. It depends on this radius, and then how big this angle is, right? So let's call this radius 2 for now, and we'll call this theta 2, okay? And then we'll, theta 1, right, R1 will be for our green sector, okay? So we have theta 2, radius 2, okay? The volume of that blue sector is going to be what? Theta, our angle, divided by 2 times our radius squared, R2 squared. Okay, that's going to give us, so this gives us the volume of our blue sector. And then if I subtract away the green sector, I should just be left with the area of the white region, right? So what's the area of the white region? Well, I have radius 1 and then theta 1 here, okay? So, and then that area is given by this. Theta, let's see, theta, well, they're the same, the angle is the same for both, right? Okay, so we don't really need to worry about the angle. Okay, we could, instead of calling it theta 2 and theta 1, we can just call it theta. Okay. So the area of that sector is just theta over 2 times R1 squared. And then what is the area of just the white region? Which, let's go ahead and color it in yellow. So what's the area of this region? Well, it's going to be the blue area minus the green area, right? So the area of that, our polar rectangle, our yellow region there, is going to be this minus this, okay, which is this. And then we're just going to play around with it and rearrange it. Okay, so maybe you can see how I've already kind of factored out a theta over 2. And then we have theta over 2 times R2 squared minus R1 squared. Well, notice that we can write R2 squared minus R1 squared. We can write that as R2 minus R1 times R2 plus R1. Okay, why are we doing that? Just because it's going to allow us to rearrange things into a more convenient form. Okay, don't worry about, how somebody figured this out. Just worry about, the meaning along the way. Okay, so what is the meaning of each of these pieces? Well, and let's rearrange it a little bit more. Okay, let's take this division by 2, and let's just put it on this term. Okay, and I'll explain why we do that. It's the exact same thing, right? These two lines are the exact same thing. It's just I've moved my fraction over here. Okay, now let's think about what each of these terms means. Okay, and that picture is the next piece. I don't want to talk about that yet. I am going to use a little bit. Let's kind of dissect what's going on. Theta, this theta term is my angle. Okay, so from here to here, that is my theta. Okay, what's R2 minus R1? Okay, that's the difference between my outer radius and my inner radius, right? So it's kind of this distance here. Okay, it's really this distance right here. And then what's R2 plus R1 over 2? I can kind of think of that. This is really an average, right? Okay, that's really the average radius on this region. Okay, so really it's kind of like choosing a radius right here in the middle. Okay. All right, and then let's kind of dissect theta a little bit. Usually we measure theta from the horizontal axis. Okay, so this theta, which is this distance here, or excuse me, this angle, the angle of this sector, I could write that as some theta 2 minus theta 1, right? Okay, theta 2 minus theta 1 is still going to give me just this angle here. Okay, and really this is the way we want to write it, because it's going to allow us to write it in polar coordinates nicely. Okay, so I'm going to rewrite this theta here as theta 2 minus theta 1. Okay. Now, how can I think of these? Okay, well, this theta 2 minus theta 1, that's really a difference of two thetas. Let's call that delta theta. And then R2 minus R1, okay, which is what? R2, R1. That's the difference of two radiuses. So I'm going to call that delta R. And then this R2 plus R1, we said that's some radius. It's like the average radius. It's a radius that kind of puts us right in our rectangle. So let's just call that R star. How about that? And again, remember, this is the area of my polar rectangle, right? Okay. All right. And let's say this rectangle is just one of many rectangles. Let's call this rectangle IJ. Okay. Then area of the polar rectangle AIJ is what? This. Okay. Okay, we could call that like, well, let's not worry about subscripts. Okay. Now, let's say I'm trying to, where's my picture? Let's say I'm trying to integrate on a region like this. I've divided my region into a bunch of polar rectangles, right? Oops. Okay, so we know how to find the area of one of these polar rectangles. Okay, and by extension, we can find the volume of the box that kind of springs from this polar rectangle. Now I want to add all the volumes above these boxes together. Okay, so when I do that, what do I get? I get this double sum here, right? So this is me adding up all the volumes of my boxes. Why do I have a double sum? Because I'm adding along my radiuses, right? So basically I kind of start by taking a single, column or whatever. And then I add up all those, and then I do the same thing going through my different angles. So I add up this way, and then I add up that way. Or, the order you add them doesn't matter. Okay. So we end up with a double sum. Okay. So I'm summing up over my radiuses and angles. Okay. And what does that look like? Looks like this. And this is looking familiar, right? This is looking like our Riemann sums for Cartesian coordinates. And now I'm just going to, this should be a delta Aij. That stands for the area of my base, right? The area of my polar rectangle, right? And we've just seen that we can rewrite that this area is equal to delta Ri, the radius of my particular box, the times the delta delta ij of my particular box. And then I have this average radius for my box ij. Okay. All right. So let's kind of bring this r term. Let's bring it right there. That's all I'm doing. From the next line, I'm just pulling that r there, okay, to get this. Okay. So this is my sum of all the volumes of my boxes, right? Okay, so that's all I've done there. Okay. Now, the last step in developing my integral is I want to take a limit, right? I want to take the limit as this area, this the size of my boxes goes to 0, essentially. Okay. So as I take the limit as that area goes to 0, what happens? Well, just like with the integral in Cartesian coordinates, my summation signs become integral signs. Okay. And then what happens as these rectangles become really small? Remember, this is like saying I'm choosing a single point in my rectangle, right? At coordinates rij star, delta ij star, or excuse me, theta ij star. And then if my rectangles are small enough, I'm eventually going to be considering every single point, right? That's kind of the intuitive idea. So my f of rij star theta ij star just becomes f of r theta. Okay. And remember, this is just some radius that puts me in my polar rectangle. And as I take the limit, I'm not considering just like a finite number of radiuses, I'm considering all my radiuses. So this rij star just becomes r. And then this delta rij becomes just dr, and then this delta theta ij just becomes d theta. Okay. Now notice the extra r term here, right? So I have a double integral. So you might see from this notation, we're going to be integrating in terms of this. This tells me I'm going to integrate in terms of r and integrate in terms of theta. What am I integrating? I'm integrating this right here. So not only do I have my function, I also have this r term. So if I'm integrating a function of polar coordinates, I don't just plug my function into the integral. I also multiply it by this r term here. Okay, so that might seem a little strange, but as we've seen from this construction, we need that r in order for this term to kind of be the area of my base. Okay, so whenever we're integrating in terms of polar coordinates, we're going to have this r term. Okay, we're going to have this extra r term. Okay. So let's just do an example real quick. Let's consider the function fr theta equals r times cosine theta. And let's say I want to find the volume, below whatever surface this gives me on this region, D. Okay, where D is the region where r is greater than or equal to 0 and less than or equal to 4, and theta is greater than or equal to 0 and less than or equal to pi over 2. Okay, so how would I integrate this thing? I set up my integral, and then my bounds are nice, right? My bounds are just these nice, simple constants. So let's say I want to integrate in terms of r first, and then theta. Okay, what are my r bounds? 0 to 4. What are my theta bounds? 0 to pi over 2. And then what do I plug into my integral? I plug in my function, and then I multiply by r. Right? So I have that, and so I have two r's, right? So really I could rewrite it as r squared cosine theta dr d theta. And then it's just integration as usual, but instead of, integrating over x and y, I'm integrating over r and theta. But from here on, the symbols don't matter. It's the same mechanics. So let's see, I integrate in terms of r, I get r cubed over 3 from 4 to 0 cosine theta. Okay, d theta. Well, let's see if I plug in my bounds there. If I plug in my bounds, what's 4 cubed? That's 64 over 3 minus 0 cosine theta. Then I integrate in terms of theta, and I get what? Sine theta. Well, let's see, 64 over 3 sine theta, and I evaluate that integral from pi over 2 to 0, which just gives me 1. So I end up with 64 over 3. That should be my volume. Whatever units cubed. Okay. I'm going to take a little break that you won't even notice. I'm back. Boom. All right. So to recap, what I'm trying to say here with all this theory is, okay, if we're given a function, let's say we're told to integrate a polar function. Okay. Let's say I'm given f r theta and told to integrate on, some the 2D region r. Okay. When I set up my integral, I plug in my function, and then instead of dx dy, I have r dr d theta. And we can change, Fubini's theorem still applies, so we can change this order of integration. Okay, we can change dr d theta as long as, we have constants here. So we can do that, but we always add this r term, okay, regardless of what our function is. Even if our function already has an r, so even if our function is like r squared sine theta, okay, when we integrate that thing, we have the r squared sine theta, sure, then we have r dr d theta. Okay, and then we combine that r with the r squared and we get r cubed. Okay, so a little strange, but you'll get used to it. Okay, so that's how we integrate when we're already working in polar coordinates. And remember, what we're doing is we're developing this tool to use, to convert to polar coordinates to make our life a bit easier. Okay, so really what we want to be able to do is we want to take a function that's hard to integrate in terms of x and y, we want to convert it to polar and then integrate in terms of polar. So we need to be able to convert our integral into polar coordinates, our function in polar coordinates. So let's, forget integrals for a second. Just think about converting Cartesian coordinates to polar coordinates. So if you've reviewed the polar coordinates video from my Calc 2 class, or just on your own, okay, maybe you recall, okay, if we're given x and y, and we want to convert into r and theta, well, r is equal to square root of x squared plus y squared, and theta is equal to tan inverse of y over x. But more importantly, we have these equations here. X equals r cosine theta, y equals r sine theta. Okay, and we could talk, this is, in my polar coordinates video from Calc 2, I talk all about this. We have a point x, y. Okay, I want to convert to r theta. Well, what is this r? This distance is my x coordinate, right? This distance is my y coordinate. So my r, by Pythagorean theorem, is square root of x squared plus y squared. Okay, and then once I have this, this triangle, I know the cosine of this angle. The cosine, well, the cosine of that angle is x over r, right? So then x equals r cosine theta. And then sine is y over r. So y equals r sine theta. So that's a quick rough explanation of why that works. But these are really important, and these are going to be the main thing we're using for converting our function into polar coordinates. If I have a function in terms of my Cartesian coordinates, my x and y, I just replace x with r cosine theta, and I replace y with r sine theta. Okay, so for example, let's convert this Cartesian equation, x squared times y, let's convert that to polar. Well, x is, I replace my x's with r cosine theta. So x squared becomes r cosine theta squared. And then y becomes r sine theta. And then I rearrange everything, collect my r terms. Look at this. Okay, so not too bad. You just replace your x's with r cosine theta, you replace your y's with r sine theta. And then that's all well and good for functions. What about, and I've kind of left this piece out, what about the integral? Okay, so we see how to convert our functions from Cartesian coordinates to polar coordinates. What about our integral? Okay, so let's forget about, we got to talk about bounds essentially, but let's say we have eventually, but let's say we have fxy dx dy. Okay, in my function, I replace my x with r cosine theta. I replace my y with r sine theta. And then I replace my dx dy, I replace that with r dr d theta. Okay. And then I have to, if I have my bounds in terms of x and y, I'm going to need to do something. I'm going to need to convert these bounds to be in terms of r and theta as well. Okay. And that again, kind of like in 15.2, you really have to just maybe draw this region that's described by the bounds in terms of x and y, and then write it, and then kind of mentally make your, conversions into r and theta. Okay, so let's go back. Let's kind of reuse a previous example. Now would be a good time to talk about this this function that we said was really hard in terms of Cartesian coordinates. Let's convert it to polar coordinates and try it. Okay, so let's copy this and take it back down to where we were, and let's try and solve this integral. Okay. 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 All right. So we're ready for this now. Okay. So I have this this integral. Okay. And whatever, we could replace dA with dx dy. So I'm trying to convert this Cartesian, this integral in Cartesian coordinates. I'm trying to convert it to an integral in polar coordinates. Okay. So let's see. I replace my, I could do this by doing, I could do this the long way, kind of by saying x equals r cosine theta. y equals r sine theta, which I just told you. We could just use this fact and convert our function here. Okay, what would this power become? What would this power here become? Well, I would have square root of r cosine theta squared plus r sine theta squared, right? Which becomes r squared cosine squared theta plus r squared sine squared theta. I factor out an r, I'm bringing out the square root. I use the trig identity, cosine squared plus sine squared equals 1, and I just end up with r. All right. Another way to do this, a much quicker way, is just to remember that r equals square root of x squared plus y squared. Okay, so I would say not only remember these, but also remember this. And then, it also helps to know that theta equals tan inverse of y over x. Just be careful with this one, because remember, tan inverse always gives you, an angle between pi over 2, negative pi over 2 and pi over 2. So you have to make sure it actually matches your quadrant that you're in. Okay. I don't think that'll come up, but use this and these when converting to polar coordinates. Okay, so our integral, our function inside our integral, it goes from e square root of x squared plus y squared. It just becomes e to the power r. Okay, and then I replace my dx dy. I replace that with r dr d theta. Okay, so I've changed the stuff inside my integral. That conversion's all done. But where am I integrating? I'm integrating on this circle, right? So we saw up at the top of the lecture that when this was in Cartesian coordinates, we could use the bounds 1 to -1 for, well, that's x, and then what, 1 minus x squared, -1 minus x squared for y. Okay, so those are bounds for Cartesian coordinates, but we're going to have totally different bounds for r and theta. And the way to convert your bounds is, again, like in 15.2, draw, or at least get a mental picture of the region you're integrating on. So what's the region I'm integrating on? X squared plus y squared equals less than or equal to 1. It's this circle, right? Circle with radius 1. Okay, so I'm integrating on this region. Well, how do I write this region in polar coordinates? Okay, it's r. Well, let's see. How do I write the circle? Just the circle itself, not the region. Okay, how do I write this circle? Okay, in Cartesian coordinates, it's x squared plus y squared equals 1. In polar coordinates, it's just r equals 1, right? Okay, so if if my region is x squared plus r squared is less than or equal to 1, then it's r is less than or equal to 1. Okay, so in other words, my bounds are 0 to 1 for r. Yeah. Okay, that gives me this region. Now, why did I say greater than or equal to 0? Well, I don't want to consider negative radiuses. I mean, we could in polar coordinates. Remember from Calc 2, you could have negative radiuses, things like that. But we're just kind of r is greater than or equal to 0, less than or equal to 1. And then what about our theta? And I'll kind of explain more in depth in a second why this works. And what about our theta? What are our bounds for theta? All we have is r, right? Well, let's see. Think about r equals 1. Okay. Really, all these points, this region is made up of a bunch of points, right? And each one consists of a radius and an angle. Okay, so we're saying the radius is always between 0 and 1. Okay, what about my angle? Well, let's see, a point here, maybe that's a certain angle, and then maybe a point here, that's pi over 4, and this point here is pi over 2, etc. And I have all these points going around until I reach 2 pi. So to make a full circle, I should have theta is between 0 and 2 pi. Okay. Now, why does this work? Okay, let's say I have this region, and let's assume, like, let's kind of pretend I'm writing down all the points by hand. I'm writing down each set r theta. Well, there's an infinite number of them, right? But if I'm writing down each point once, okay, I'm going to write down combinations like this, r and theta, and all my r's are somewhere between 0 and 1, right? And all my thetas are between 0 and 2 pi. So if I take all the possible combinations of r between 0 and 1, and then theta between 0 and pi, I'll eventually end up with all my points. Okay, so that's kind of how I arrive at the bounds. So my bounds for this integral are here. Okay, let's see, I'm integrating in terms of r first. So I have 0 to 1 for r, 0 to 2 pi for my theta bounds. Okay. And now this integral is really easy to do, right? You just have e to the r times r. I'm integrating in terms of r. Well, this is, we could do this with integration by parts, right? So we're still using those tools from Calc 2. Okay, integration by parts. This would give me what? R e to the r minus the integral of e to the r from 1 to 0. What? E to the r times r minus 1 to 0 d theta. Okay, so let's see. When I plug in 1, I get e to the 1 times 0 minus e to the 1 times negative 1. Okay, and e to the 1 is just 1. So I get e, the integral of e in terms of theta. Well, e is just a constant. I can pull it outside. And then I just get e times theta integrated from 2 pi to 0. In other words, I get 2 pi times e. Okay. Let's do one more example of, I'll take one example from the back of the book. Let's see, do I have more problems down here? Not a good one of converting. So let's do one more example of converting from Cartesian to polar. How about let's see, let's pick a good one. How about this? Let's do number 8 from the textbook. So we're told to integrate 2x minus, so we're given a integral in Cartesian coordinates, okay? And we're told R is the region in the first quadrant enclosed by the circle x squared plus y squared equals 4, and the lines x equals 0, y equals x. So we're again, our region is the first region in the first quadrant enclosed by these 3 curves. Okay. All right. Converting the stuff inside the integral is easy. That's the kind of low-hanging fruit. We can convert the stuff inside the integral easily. My x becomes r cosine theta. So I have 2r cosine theta minus r sine theta. My y becomes r sine theta. All right. And then my dA, well, you know, if I was going to write it as dx dy, okay, that becomes r dr d theta. Okay, replacing dx dy with r dr d theta. Okay, and then I could, you know, simplify all this. So I get what? 2r squared cosine theta minus r squared sine theta. I factor out the r squared. Okay. Now that's fine. That's our stuff inside the integral. What about the region? So again, we have to just kind of draw our region and then find a way to express it in polar coordinates. So what is our region? Okay, we're told we're confining ourselves to the first quadrant. Okay, so I'm just considering that first quadrant. And then we have the region bounded by the circle, x squared plus y squared equals 4. Okay, so a circle with radius 2, right? That's my horrible circle quadrant. And then we also have the lines x equals 0, which is just that x-axis, or next to me, the y-axis. We have this line here, and then y equals x, which is this diagonal line. Okay, so there's only one region that is enclosed by these 3 curves. Okay, what is it? It's the shaded region, right? Okay. Anything else is not gonna meet our 3 conditions. Okay, so we have this region. Okay. Now, essentially, I just need to find a way to write this in polar coordinates. What is this in polar coordinates? Okay, I need to write this in terms of r and theta. Okay, so where are my angles? Okay, what are the angles of this region? Well, it starts at this angle. What is this angle? Well, maybe we know just from experience that the line y equals x, that's like at the 45-degree angle, right? So our region starts at, what is the 45-degree angle? Pi over 4. Okay, and where does my region end? Well, it ends at the y-axis, or the vertical axis, which is what angle? Pi over 2. Again, I'm measuring the angle from the horizontal axis, right? So this is pi over 4, and then that one is pi over 2. All right, what about radius? Where do my radiuses begin? Well, I have all these points, right? So my radius, it looks like, starts, you know, from the, you know, very center. It starts down here at 0. And then where does it go? We stop at this outer line. What is this outer radius? Well, from our outset, we know, okay, this is the circle with radius 2. So this radius is 2. Okay, so our radius goes from 0 to 2. So to finish, I have my bounds now of my integral. Okay, what did we say our function was? R squared 2 cosine theta minus sine theta. And then let's see, we did dr d theta, right? So I put my r bounds first. We said there's 0 to 2. And our theta bounds next, pi over 4 to pi over 2. Okay. Then I just integrate, and there's nothing hard about this integration, right? This r squared becomes r cubed over 3, and I evaluate it, and I get, what, 8 over 3. That should be right, yep. And then I got, okay, 2 cosine theta minus sine theta, okay. D theta, I integrate in terms of theta. And what do I get? I get 2 sine theta plus cosine theta. From pi over 4 to pi over 2. Okay, and I'm just not going to finish this. Evaluate it. You can pull out these constants and write it as 16 over 3 times that stuff. The rest is just plugging in those pi's, which I'll let you guys do on your own if you like. All right. And we can do more examples like this in our problem session on Tuesday. But let's go ahead and move on to our kind of last topic of the section. So just like Cartesian integrals, okay, these integrals in Cartesian coordinates, how did those develop? We started by doing very simple integrals on just rectangles where my bounds were just constants, which is essentially what I was doing. This is what we had here, okay, just an integral, the bounds were just constants. And then what was 15.2? The 15.2 was like these Cartesian integrals, but then, the regions were a bit more complicated and we had to put functions in these bounds, okay? And the polar integrals develop in the same way. Maybe I need not just constants for my bounds of a polar integral. Maybe I need functions. Okay, so remember when we had, again, this is kind of just an example of what I was just saying. If we had this type of integral in Cartesian coordinates, the bounds for, I could write this as this region as with y bounds 0 to x squared, and then x bounds 0 to 4. Or I could write it the other way with x bounds square root of y to 4 and y bounds 0 to 16, which is kind of what we talked about in the problem section today. Okay, now that's the Cartesian example, and we're going to do a similar thing for polar integrals. Okay. So again, the problem is we're going to use this type of technique. Okay. So we see here we use this technique in the Cartesian coordinates when our region is not just a nice rectangle. Okay, this isn't a nice rectangle because we have this kind of this almost triangular region. It's kind of bounded above by that parabola. So just like with Cartesian coordinates, we might have a region that's not a nice polar rectangle, right? So a polar rectangle would be something like this, just kind of a quadrant of a circle. But what if like this edge is not that nice straight line? What if it's something like that? Okay, and then something like this. Okay, so maybe our R bounds, are these nice constants like R equals 1 to R equals 4, but then my theta bounds, my bounds on this angle here, okay, it's not clear what this angle is. Maybe I have to write this angle as a function of R, you know, and like, so this angle, you know, my starting bound would be a function of R, and then my ending bound for theta would be a different function of R, something like that. Okay. Or maybe this side is a nice constant. Maybe this is like the angle pi over 6. But then I end on a weird function. So maybe my bounds would be like pi over 6 to this function g of R. Okay. All right, so we have those types of scenarios. So an example would be this problem, which is just, again, taken from the back of the book. Find the area of the region enclosed by these cardioids, r equals 1 plus cosine theta and r equals 1 minus cosine theta. So there's a bit to kind of unpack here. First of all, we're told to find the area, okay? And we're used to thinking of these multiple integrals as like volumes, right? But remember, let's say I have a region, you know, let's say I have this 2D region here, call it D. And what do I get if I integrate just the number 1? Let's talk about Cartesian coordinates for a second. Let's say I integrate the number 1 over that region. What do I get? Well, it's going to give me a number, just like any other integral, but that number is actually going to be the area, not the volume. And it's going to be the area of D. Why is that? If I integrate the number 1, it's like integrating, okay, what is 1? It's just the function with a constant height. So I just kind of get one of these generalized cylinders of height 1. So it's like a cylinder of height 1. What's the volume of that cylinder? It's 1 times whatever the area of the base is. Okay, so this integral, it's going to give me a number, and that number is just going to be the area of the base, right? So I can find the area of a region just by integrating the number 1 over the region. And I can do the same thing in polar coordinates. If I want to find the area of a region, okay, let's say D, or let's call it R. Okay, let's say I want to find the area of a region in polar coordinates. I just integrate the number 1 over that region. But remember, when I put in my dr d theta, it's not just dr d theta, it's r dr d theta, right? So this integral will always give me the area of my region. Okay. So when I'm told in this problem to find the area of the region enclosed by these cardioids, essentially what I'm going to do is I'm just going to integrate the number 1 r dr d theta. And then the problem is finding the bounds. Okay, the bounds are the complicated part of this question. Okay, obviously the function is not very complicated. Okay, so what are the bounds? Again, we need to just draw our region. Okay, so there is maybe a little bit of simple graphing of polar coordinates, and honestly, like on your tests, I'm going to give you, this polar stuff, we need it, but it's obviously not, I haven't given, and it's not in the scope of this course to give a ground up explanation of polar graphing again. So, you're supposed to know it from Calc 2, but realistically, I know that not everybody is still, perfect with these polar graphs. So any graphing I give you is going to be very simple, like these. I think these are fine to give you. Okay, so you need to be able to graph these simple things on a test. You can't use software. If you're working on homework, try and graph it on your own and then use, Desmos or whatever to kind of check your work. That's fine. I think that's fine. Okay, so let's graph these things and kind of look at the region we're dealing with. So r equals 1 plus cosine theta. Okay, so now I'm going to try and graph this myself, which, let's see, r equals 1 plus cosine theta. So when theta is equal to 0, we're at, what, 2? And then when theta is equal to pi over 2, we're down to 1. Okay. When theta is equal to pi, we're at 1 plus negative 1, which is 0. Okay. And then 3 pi over 2. Okay, we're down to negative 1. Okay, so our cardioid 1 plus cosine theta essentially looks like this. And the scale might be a little messed up, but this is essentially what it is. Okay. What about 1 minus cosine theta? Okay, well, let's see. At theta equals 0, we're 1 minus 1, so we're here. Okay. And then at theta equals pi would be at 1 minus negative 1, so 2. So it's kind of, it's the flipped, it looks like it's the flipped cardioid. And let's do this one in blue so we can keep track of what's what. Okay. All right, so we're told to find the area of the region enclosed by those two curves, so kind of in between those two curves. So what region are we talking about? Well, let's see. Looks like we need this and this. Okay. So we can use symmetry a little bit. Honestly, we could do this just as a single integral. Let's see, how would they want us to do this as a double integral? Okay. We know we want this r dr d theta. I want to integrate. Okay, what angle do I want to integrate from? What we could do is just find the area of one of these circles and then multiply it by 2 to get both. Okay, so let's see, let's just do the integral for this top circle here. Okay. And, I say it's a circle. It might not be exactly a circle, but it's, at least symmetrical around that line. Okay. So what is that area? Okay, what would my bounds for that be? Well, I would start at theta equals 0, and then I'm making a full, well, let's see, would it be a full circle? Let's see, here, this for this function, this is when this function equals my theta angle equals 0, and then at pi over 2, I'm here. My baby is crying in the background. Hold on, let me pause real quick. Okay, I'm back, and it was a good break because it gave me an opportunity to actually think about what this answer is. I was getting a little stuck thinking about it on the fly. Okay, so we found our two cardioids and we're trying to write some bounds. Okay, so I'll take a little shortcut here. We're trying to find this shaded region, this shaded area here. Okay, well, we're going to use some symmetry and we're saying, okay, these two things look like they have the same area. Okay, so let's just find the area of one of them and multiply it by 2. Okay, so 2, whatever our integral, whatever our bounds are. Okay, and let's go a bit further and say, well, this left side, it looks like it's the same area as this right side. So let's just find this one side, the area of this one side, and then multiply that by 4, and that should give me the total. Okay, so what are the bounds for this one side? Okay, what is my radius range between, well, what's the smallest my radius is in this region, and what's the largest it is? Okay, and let's kind of draw this again a bit bigger down here so you guys can see. Essentially what I have is I'll go ahead and draw my cardioids again. Boom, boom. And maybe it's clear that these probably aren't circles, right? Some kind of like double teardrop shape. Okay, and let's again do one in a different color. Okay, and pretend these are completely symmetrical things. So I'm trying to find this area, and I'm going to multiply it by 4. Okay, so I'm trying to find my R bounds and my theta bounds. Well, let's see. My R, it's bigger than 0, right? If I had radius 0, okay, I'd be down here. Oops. And then what's the largest my radius can be? Don't think about it try and think about it in terms of a function. Well, my radius is always less than whatever that curve is, right? My radius stops at that curve. And what is that curve? That curve is R equals 1 minus cosine theta. That's that white curve, right? So let's do 0 for the bottom of my lower bound for my R. And then my upper bound should be 1 minus cosine of theta. Okay. And then what about my angle? My angle, so now I have like my function here. So my other bounds should just be constants. All right, so what are my angles here? Well, I'm starting here at theta equals 0, right? That's like, right along this axis. And then I'm moving in this direction. And where do I stop? I stop at this angle, which is pi over 2. Okay. So if I integrate this thing with these bounds, that should give me, and then multiply by 4, that should give me my area of that whole shaded region. Okay. So last step, let's go ahead and integrate that. Okay. So I have the integral 1 times r. Let's just go ahead and simplify this. It's just r dr d theta, right? So I integrate in terms of r. I get r squared over 2. Integrate, evaluate it for my bounds. When I plug in my bounds, I get what? 1 minus cosine of theta squared over 2 d theta. Okay. And let's go ahead and pull out the 1/2. And what does 1 minus cosine squared become? 1 minus 2 cosine theta plus cosine squared of theta, right? D theta. I integrate all this. well, let's go ahead and convert the cosine squared. We could write as what? 1/2 1 plus cosine 2 theta. That's the what? Double angle identity. And the rest of the stuff stays the same. Integrating theta minus what? 2 sine theta plus 1/2 theta plus sine of 2 theta over 4. Evaluated for my bounds. Plug in my bounds. And those go from what we said, 0 to pi over 2. So we get pi over 2 minus 2 plus pi over 4 plus sine of 2 times pi over 2, so 0 over 4. Okay, and then I subtract the bounds when I plug in 0, and those should all be 0. So I should just end up with this, which is equal to what? Pi minus 4 plus pi over 2. So really 3 pi over 2 minus 4. Okay, and that should be the answer. Double check that on your own. This is a bit of a slog, obviously, but it's not too bad. Once we have our region. So check that on your own and let me know if you get something different. All right. Good luck with that, and we'll cover the hard examples and the hard problems from the homework in the problem session.